Alright, so today we're going to be doing 6.4, which is going to be inverse functions and relations. So inverse notation, there are several ways to indicate inverse notation, which are listed here. An inverse relation is any relation where the elements of an ordered pair have been switched. So you take some relation and you flip the x's and y's, and that resulting relation is the inverse to the original. Now if we flip the x's and y, we also flip our domain and range, right? Because they are the collection of all the possible x's and y's. So the domain becomes its range, the range becomes its domain. Now two functions, f and g, are said to be inverse functions if both of their compositions yield the identity function y equals x. So what that means is, if you take f of g of x and it comes out to be x, and you take g of f of x and it comes out to be x, that means that those two functions must be inverses, okay? We'll talk a little bit more about that in 6.5. And every single inverse function will be a reflection over the line y equals x. Not all functions have inverse functions, but they always have at least an inverse relation. Remember, a relation is just a collection of numbers, points, an equation. A function is a special type of relation that passes the vertical line test. Speaking of the vertical line test, this is a test used to determine if a relation is a function. If all vertical lines intersect the graph no more than once, then the graph represents a function. For every x such that you try, there is only one y that is a function, okay? Now the horizontal line test can determine if a function will have an inverse function. So if it passes both the vertical and the horizontal line test, that means that it is a function and its inverse is also a function. If it does not pass the horizontal line test, its inverse is not a function. And a one-to-one function passes both tests. As you can see here, a cubic function passes both the vertical and the horizontal line test, but a quadratic function only passes the vertical line test. Therefore, the inverse of a quadratic function is just a relation, not a function. Now, a one-to-one function, every x maps to exactly one y, and in a many-to-one, a normal function that isn't one-to-one, one x can map to multiple y's, just like a quadratic does. Okay, quadratic is a classic example of this. Important note here is that when we talk about reciprocal functions in this class eventually, they use a very similar notation, okay? This is inverse notation on the right. On the left is reciprocal. You see the difference? The negative one's in a different spot. So just be sure not to mix those two things up because they are different. They have different meanings. All right. So the easiest way you can find an inverse is by mapping. So we're going to be using a lot of mapping today. But first, let's just talk about the simple example of this. So we have a relation R given to us by these coordinates. Now to find its inverse, all you have to do is make the y's the x and make the x's the y. Oops, that's wrong. I didn't even write it right. There we go. So it's going to look like that. Now I'm going to go ahead and graph both of these, and I'm going to graph the first one in green, and I'll graph the second one in red so you can follow along. So in green, we have 0, negative 1. We have 2, 0. We have 3, 2. And we have 4, 3. All right. So now we're going to go ahead and graph the relation. So that's negative 1, 0, 0, 2, 2, 3, and 3, 4. So can everyone see the relationship between these two relations? You notice that they're a reflection over the line y equals x. That means that they are inverses. Now we're going to look at each of them and see if they each individually pass the vertical line test. Does the first one pass the vertical line test? The green one? Yes, it does. Oh, yes. So to not pass it, it just means that you'd hit more than one point on the function if you drew any vertical line. And it doesn't have any issues like that. There's no repeating x's, so there's nothing to worry about. And does the one in the red, the inverse, pass the vertical line test? Yes. So you're just looking to see if there were any double points that we'd hit if we drew a vertical line. Alright, so now we're going to go ahead and come up with an inverse together. Before we get into any of these examples, I just want to mention something real quick. Oftentimes, like on your homework, instead of y, they might use f of x or g of x or something like that. Always change it to a y. Okay, if they give you anything but that, if they give you f of x, g of x, h of x, you're just going to first change it to a y, which I've already done in this case, but I just want to mention that ahead of time. Now, once it's in the form where you have a y and an x, to find the inverse, first thing you're going to do is you're going to rewrite the equation, but you're going to flip the x and the y. Does everyone see what I did there? I took the equation, I rewrote it, but my x and y have been flipped. Does everyone see what just happened? So now from here, I'm going to solve for my new y. So I'm going to subtract 4 on both sides. And then lastly, to completely solve for y, I'm going to divide both sides by the -3. That's going to give me y equals -1/3 x plus 4/3. Okay, because there's an implied 1 in front of that x, of course. And that's going to be my inverse. Okay, we just found the inverse. Once you've identified that it's the inverse, you're going to put that notation on it, that -1 notation, just like that. So we've just come up with the function's inverse. Now the good news is we're going to talk about a few different ways we can go about graphing this, and sometimes it's a little bit easier, sometimes there's loopholes and other ways we can go about it. So first thing we're going to do is we're going to try to graph the original function. Does anyone know what kind of function this is? Linear, quadratic, cubic?
Linear.
It is linear. But the problem is, you're used to seeing linear functions in this format, right? Y equals mx plus b. Does that sound familiar?
Yeah.
What's the problem with this equation right here?
3 and the 4 need to be swapped.
Good. The 3 and the 4 need to be swapped around, right? Does everyone?
I have a question.
Sure.
So when you did the 4/3, where did the negative go?
Good question. We divided a negative by another negative,
Right.
which made it positive. Does that make sense? Okay. So does everyone understand why I rewrote the original equation in this form and why it's helpful to us? Okay. I just flipped the m term and the b term. And now I'm able to graph it because this is my y-intercept and this is my slope. Okay. So we start at our y-intercept and then I go down 3 and over 1. Down 3 over 1. And I end up, yeah, go ahead.
How do you get to the equation you just have right there?
That's just me flipping these two terms around to get into this form right here.
Okay.
Because it was written with the y-intercept first and then the slope, so I just flipped them around so that it's in the form I need it to be in to graph it. And if you ever get stuck on this too as well, you have access to Desmos, so you can always graph in there as well if you feel more comfortable with it and check the table and all that. So now from here, we're going to go ahead and graph the inverse, the one in the pink here. So the slope and the y-intercept are fractions. So the y-intercept 4/3 is approximately, if you're wondering, it's approximately 1.3. Okay, so we're going to start on the y-axis at about 1.3. And then we're going to go down 1 unit and over 1, 2, 3 units. And then I can find another point this way by going up 1 over 1, 2, 3 to the other direction. So that's my inverse equation. Now, by looking at it, you can tell that they're inverses. Anyone see why that is? It's reflected over what line? See how they're both reflections over the line y equals x of each other? That's how you can verify that you've done it correctly. Now we want to determine some information about this. Does it pass the horizontal line test? So if we look at the original function, the one in the red graph, would that one in the red graph pass the horizontal line test? Who says yes? Anyone? Does this graph in the red pass the horizontal line test? Yeah, it does, right?
Yeah.
It's just a linear function. There's no reason it wouldn't pass the horizontal line test. It's only going to hit one point. And then all linear functions all have a domain of all real numbers, as well as a range of all real numbers. And that's because it goes left forever, right forever, up forever, and down forever, okay? Is the one in the red a function? It's a function if it passes the vertical line test. So is it a function? The one in the red? This red graph, is it a function? Yeah, it's a function. Now, when you go to identify the characteristics about its inverse, your old range is now your domain, and your domain is now your range. They flipped range and domain. So you don't have to algebraically find it, you can just flip the range and domain. And in this case, since they're both the same, it doesn't matter, but the range and domain flip. Now, if your original function passes the horizontal line test, your inverse is also a function. So, is the inverse a function?
Yes.
Yes, because we passed the horizontal line test. And if that doesn't make sense to you, you can also see that the graph in the green obviously is a function, right? It passes the vertical line test. It doesn't have any duplicating y values that go from the same x and whatnot. So, any questions about that? Okay. Ready to try the next one?
Not really, but
I mean, does anyone need more time on the slide? All right. Anyway, so we have the equation y equals 2. Does anyone know what this graph looks like if I were to graph it?
it's a straight line.
A straight line, is it horizontal or vertical? Horizontal. So the inverse, any expectations on what you think the inverse is going to be? A vertical line. Now, normally, when we do inverses, we flip the x and the y, right? But is there any x for me to flip here? No, so only the y changes to the x. So this right here, and I should probably do it in another color, is the inverse. Hang on, I'll rewrite it. X equals 2 is the inverse, okay? And you can't, there is no y, so that's just the inverse. So, the one in the blue, like you said, it's a perfectly horizontal line at the value of y equals 2. And then in the red, that's a vertical line. And do you see how they're inverses and they're reflections over that line y equals x? Everyone see that? So, let's talk about analyzing this. We're looking at the original graph, that's the one in the blue. Does this original blue graph pass the horizontal line test?
Quite so close.
No. Because if I drew a horizontal line right here, it's going to hit more than one point, right? So it doesn't pass the horizontal line test. So automatically, I know that my inverse is not a what? It's not a function. And you can see that it's not a function because it doesn't pass the vertical line test. What is the domain of the one in the blue here, the original? It goes to the left and the right forever, right? So its domain is? Good, all real numbers. Now, range, does this function go up and down forever? No, it only ever takes on what y value? 2. So its range is simply just 2. Now, do I need to go ahead and analyze the red graph for the domain and range? Or is there an easier way to find it?
Don't you just take up the range and make it the domain for that one?
Good.
And vice versa?
Exactly. So your original domain is now your range, and your original range is now your domain. So you can just flip the range and domain, which makes sense because domain's all the x, range is all the y, x and y's flip when we do an inverse, so of course the range and domain are going to flip as well. So do we have any questions about that? Before we get into this problem, I am going to be pulling up Desmos and explaining some stuff about this one. Now, the first thing we're going to do here is, if I want to find the inverse, what's my first step?
You switch the y and the x.
Good, we switched the y and the x. And then my goal is to solve for the new y, right? So we add 5 to both sides. We get x plus 5 is equal to y squared. And to get rid of a square, you take the what?
Square root.
Good. And if you're going to take a square root, you have to put in a plus or minus. So that's going to be y equals the square root of, or plus or minus the square root of, x plus 5. Now, what I'm going to explain to you today, I'm going to explain the reason the plus and minus is so important, okay? So for a second here, I'm going to pull up Desmos, okay? So, in Desmos, as you can see, I graphed the original function. Everyone good with where that came from? Now I'm also going to graph the line y equals x, because that's the line that we know that the inverse will reflect over. Now, if I go to try to graph the inverse that we just came up with, y equals, to graph the inverse, I have to do a plus or minus, right? But you're going to notice that there is no way to graph a plus or minus in graphing software. So what you actually have to do is you have to do square root of x plus 5, so the positive version, and also the negative version. Does everyone see that, how I had to graph it in 2 pieces? Does everyone see why both those pieces are important? What's wrong if I only have one piece?
Then it won't be like the whole continuous line.
Yeah, it's not the whole inverse. But oftentimes, you'll see people use only a piece of this as a graph of the inverse, because if I only have a piece of it, it is a function, but the 2 pieces together are not a function, right?
Because it hits both 2 points.
Exactly, it wouldn't pass the vertical line test. If I had one piece, it would, but 2 pieces, it doesn't. So this is one of those situations where you're getting into higher level math, where you're seeing the constraints that we have on some of the software we use, as well as understanding the manipulations of things that we use so that things work out the way we want them to. So you'll see people say, I'm only going to use this piece of it, so it's an incomplete inverse of the original function. But if you want to have the complete inverse, you have to have the whole thing. Yes?
Sorry, what does the horizontal line test tell you again?
Sure. So the horizontal line test tells you if its inverse will be a function. So see how, for example, this red graph right here, see how this wouldn't pass, it would pass the vertical line test, but it wouldn't pass the horizontal line test? For that reason, we know its inverse won't be a function, which we just kind of showed in that case.
Got it.
Okay. So, now that we've talked about all that, we're going to go ahead and make a table for the original function, okay? So I'm going to just go from -2 to 2, keep it simple. And if you're not sure what bounds to use, you're welcome to use Desmos tables to figure it out. And I'll explain some other procedures and things we can do to figure that out. So to find this corresponding side of the table, all I'm going to do here is I'm going to plug these values into this function right here, okay? So what's -2 squared?
4,
What's 4 minus 5?
-1.
Good. So we got -1. If you plug in 1, we get 1 squared minus 5, which is -4. If you plug in 0, you get -5. If you plug in 1, you get -4. And if you plug in 2, you get -1. Now, do I need to go plugging values into this inverse? Which I forgot to write that it's the little inverse. Do I have to do that? What's the easier way to do this?
Switch it.
Just switch it. Why go through extra work when you don't have to? Work smarter, not harder, right? So I can just flip the table. So the good news is, if your inverse is complicated, you don't have to worry about coming up with or plugging things in, graphing that. All you have to do is flip the table from the original function and you'll have the inverse. Does that make sense? So I'm going to graph the original in blue. I'll graph the inverse in green. So we have -2, -1, -1, -4, 0, -5, 1, -4, and 2, -1. So this is the graph of the original function. Now I'm going to go ahead and graph its inverse using this table. -1, -2, -4, -1, -5, 0, -4, 1, and -1, 2. So visually, can you confirm that it looks like the inverse? Is it a reflection over that line? Yes, it is. So now we're going to analyze domain and range. The original function, the one in the blue, does it pass the horizontal line test? No. If I drew a horizontal line through this blue function, wouldn't it hit more than 1 point? Yeah, right, it would hit 2. So it doesn't pass. Now the domain for any quadratic function, as you can see, this function gets wider and wider as it goes on, eventually taking on every x. So its domain is all real numbers. But its range is restricted, because does this blue function go down forever?
No, just to -5.
Good, it goes down to -5, but it goes up from -5, right? And is the one in the blue a function? As in, does it pass the vertical line test? It passes the vertical, but not the horizontal. Does that make sense? Because you could draw a vertical line through this function anywhere and it would only hit 1 point. But if you were to go about and draw a horizontal, it's going to hit more than 1. So vertical versus horizontal. So quadratics are always going to pass the vertical, but not the horizontal. Is its inverse going to be a function? No, because it didn't pass the horizontal line test, inverse will never be a function. What is the domain of my inverse?
-5 to
Good. And what's the range of my inverse?
negative to positive.
Good. Starting to get the hang of it now, a little bit. The difference between the two function tests. You have to make sure you know those. Let's go ahead and look at this one here. So right off the bat, I think of this. See if you can recognize it. Does that form look familiar to you? You've seen it before. I know you have because I showed you. Anybody know what we call this form?
Which one?
That I wrote up here?
Oh, vertex form.
Very good. This is vertex form of what type of function?
Quadratic.
Quadratic.
Good. That's vertex form of a quadratic. What do you notice about the given function?
It's vertex form of a quadratic.
It's vertex form of a quadratic. So we're going to come back to that and see. We're going to talk about why that's important. But first and foremost, we have to find this inverse. So I'm going to start by flipping my x and my y. What's my first step in getting y by itself?
Subtract it 2.
Good. How do I get rid of a square?
Square root it.
That leaves me with plus or minus the square root of x minus 2 is equal to y minus 1. Last thing I have to do is add 1 to both sides. That gives me, I'm kind of running out of room here, hang on. That gives me y is equal to 1 plus or minus the square root of x minus 2. Good news is you don't have to graph that because we have an easier way to graph, right? So now we're going to go ahead and graph the original function. And this is where its vertex form comes in handy, okay? So, don't we know what the vertex is by just looking at this? Remember h and k are the vertex? Is this coming back to you a little bit? You know what? So the vertex you put in the middle of the table and it's 1, 2. Remember, it's always the flip of this and then whatever this is.
Yeah.
Okay, I just want to make sure like I'm not like totally confusing you guys. You know where this comes from, right? So now with the rest of your table, you can just backtrack, remember, and then go forward, and you have a table that's symmetric. Hopefully this is ringing some kind of bell to you guys. Yeah. Okay. And now you would just then plug these values in, okay? So in this case, if I plug in 0, I end up with 3. If I plug in 2, I end up with 3. If I plug in 3 minus 1, okay, that's going to be 6. And if I plug in -1, I get 6 as well. Do I have to do any math to get the inverse table? No. No. It's probably your favorite part of this, right? You just, look at that. Easy. And now we can go ahead and graph both of them. I'm going to do the first one in blue. 6 isn't on the graph, so I'm just going to estimate, like up here. 0, 3, 1, 2, 2, 3, and 3, 6. And then we have 6, -1, 3, 0, 2, 1, 3, 2, and this one. Like that. Do they look like inverses? Would this give you be a red flag if you saw this and think you did something wrong?
Yeah. I don't know.
Do these look like reflections over the line?
Symmetrical.
Yeah, they're symmetric. So you just want to verify they look like they look like inverses, okay? So if something looks completely off, then you know you might want to look over your work. Domain, so we're looking at the blue function. Does the blue pass the horizontal line test?
No.
But it passes the vertical line test. Domain, all real numbers of the blue, and the range is from 2 to positive infinity, right? So therefore, domain of the other one is going to be 2 to positive infinity. Range is going to be all real numbers, and it is not a function.